Welcome back to Honors Calculus. In this video, we're going to continue our discussion on differentiation rules with the ideas called the product and quotient rules. Oh, I'm being blurry today. I apologize. Let's just get my blurry head out of the way and dive into the math. The product rule says very simply that if we have two differentiable functions f and g, then the derivative of the product fg is the derivative of the first f prime times the second g plus the first f times the derivative of the second g prime. And just like we saw in the last video, if we can prove this in general using the limit definition of the derivative, then we have it and we don't have to go back to limits anymore in differentiating. So by definition, the derivative of fg is the limit as delta x goes to 0 of fg evaluated at x plus delta x minus fg evaluated at x all over delta x. And of course, a product of two functions is literally evaluate each function at the given point and multiply them together. So fg at x plus delta x is just f of x plus delta x times g of x plus delta x. And fg evaluated at x is literally just f of x, g of x. All right. Up next, I'm going to employ mathematician's best friend. I'm going to need a bit more space. Let's slide that equal sign way over here. We're going to look at the limit as delta x goes to 0. I am going to do absolutely nothing in the messiest way possible. Mathematician's best friend. If you have a mess and you're not sure what to do with it, see if there's a creative way of adding 0. And in fact, that's exactly what I'm going to do. Let's leave the first term in the numerator alone. So we'll have f of x plus delta x times g of x plus delta x. And now, adding 0 creatively, I'm going to add and subtract exactly the same thing in a way that's going to turn out to be incredibly useful. And that thing is going to be kind of the hybrid of these two terms. F of x, g of x plus delta x. Again, I cannot just arbitrarily subtract f of x times g of x plus delta x. But if I subtract it and then immediately add exactly that same thing, then I haven't done anything except take something that was already messy and make it excruciatingly painfully messy. This is one of mathematics' favorite tricks. When you're not sure what to do, see if you can add and subtract the same thing and make something that looked like a mess look even more like a mess. And then maybe you can simplify and get things to work nicely. And in fact, that is my next step. All right, let's move this way up on the page so I have some space to keep going. My next step is going to be to group the first two and the last two, right? Adding and subtracting the same thing does nothing. the way to make it do something is to find a way to split up those two things that would cancel each other out. So I take the negative one and group it with the first bit. I take the positive one and group it with the second bit. And this becomes useful because you may notice that those first two terms have a g of x plus delta x. Those last two terms both have an f of x. So the next thing I'm going to do is some factoring. If I take f of x plus delta x minus f of x, I can factor out the g of x plus delta x. And if I take and factor out the f of x, it will leave behind g of x plus delta x minus g of x. And the whole thing is still over delta x. Right. Now let's split things up further. We have a fraction, we have addition going on in the numerator of the fraction. We can split this fraction apart and write this as the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x all times g of x plus delta x plus f of x times g of x plus delta x minus g of x all over delta x. Right? Just splitting that fraction up. And sure, I took one of the factors and I pulled it out of the fraction because it makes things look nicer. And this is also usually the point where people start to look at it and say, yeah, I can kind of see what's going on here. Because now I'm taking the limit of a sum. And the limit of a sum is the sum of the limits. So this is the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x times g of x plus delta x plus the limit as delta x goes to 0 of f of x times g of x plus delta x minus g of x all over delta x. And now the limit of a product is the product of the limits. I have to worry about that on the first limit. On the second limit, that f of x is constant with respect to delta x. And to save myself a little bit of writing, I could just bring it out. But I'm going to try to write this symmetrically. I think it'll be a little bit easier to follow. Right, we can split this up further as the limit as delta x goes to 0 of f of x, why do I keep doing that? X plus delta x minus f of x all over delta x times the limit as delta x goes to 0 of g of x plus delta x plus the limit as delta x goes to 0 of f of x times the limit as delta x goes to 0 of g of x plus delta x minus g of x all over delta x. Right here again, I'm just taking the limit of the product and splitting it up as the product of the limit on both pieces, here and there. And now that I've done that, here it all just falls together. My first term here, right here. This is the definition of the derivative of f. My second term here. I'm evaluating, I can just plug in delta x goes to 0, and I get g of x. My third piece right here, delta x doesn't even show up. This is just f of x. And my last piece, go the right way. My last piece here, this is the derivative of g of x by definition. So everything falls away, and I'm left with f prime times g plus f times g prime. Building on the product rule, we're going to next go to the quotient rule. But before we can get there, I need a fairly straightforward lemma. Let's let g be a differentiable real-valued function and non-zero. Of course, non-zero is important because I'm going to be looking at its reciprocal, 1 over g. The derivative of 1 over g is the negative of g divided by g squared. If you look in the typed notes, I prove this lemma using the limit definition of the derivative. But as a shortcut, I want to show you that we can actually prove this using the generalized power rule. We know that the derivative of x to the n is n times x to the n minus 1. So assuming that this will work for negative values as well, and it will, I can get that the derivative of x to the negative 1 is negative 1 times x to the negative 1 minus 1 should be negative 1 times x to the negative 2, and then using the properties of negative exponents, this is negative 1 over x squared. Now from here, the derivative of 1 over g is the derivative of g to the negative 1 power using properties of exponents. And now I can use the chain rule. Remember, the chain rule says that if you want to take the derivative of a function, you take the derivative, evaluate it at that point, and then multiply by the derivative of the inner function. So the derivative of x to the negative 1 is negative 1 over x squared. Evaluate that at g, and then multiply by the derivative of g. Negative 1 over g squared times g prime. And all of that together gives us the result of the lemma. Now that we have the lemma, we can go on to the quotient rule. Let's let f and g be differentiable real-valued functions. Let's assume that g is non-zero and take the derivative of the ratio f over g. And my claim is that this is going to be f prime times g minus g prime times f all over g squared. And to prove this, I will combine the lemma with the product rule. The derivative of f over g is the same thing as the derivative of f times 1 over g. And by the product rule, that's going to be the derivative of f times 1 over g plus f times the derivative of 1 over g. Right? The derivative of f is just f prime. And by our lemma, the derivative of g is the negative of g prime over g squared. If I take that first fraction and multiply top and bottom by g, I'll have some common denominators. And then I can subtract across the numerator. And now we have the quotient rule. And the quotient rule is very powerful. With the quotient rule, of course, we can take the derivative of rational functions. For example, let's take a look at the derivative of x plus 1 over x squared minus 1. And notice here that this is a rational. Let's set f as x plus 1. Let's set g as x squared minus 1. These are both polynomials, so we can take the derivative of each of those relatively straightforward. Derivative of x is 1, derivative of 1 is 0, so f prime is simply 1. Derivative of x squared is 2x, derivative of minus 1 is 0, so g prime is 2x. And then the derivative here, by the quotient rule, will be f prime times g minus f times g prime all over g squared. Right? F prime is 1, g is x squared minus 1, f is x plus 1, g prime is 2x, g is x squared minus 1, and is being squared. Okay. Multiplying everything out here, we have x squared minus 1 minus 2x squared minus 2x all over x squared minus 1 squared. Looking for some common factors. Let's see, this is going to be minus x squared minus 2x minus 1 all over x squared minus 1 squared. And things here factor further. there's a common factor of -1. X squared, 2x, and 1 factors to x plus 1 times x plus 1. X squared minus 1 factors to x plus 1 times x minus 1. And since this whole thing is being squared, we can distribute that and square each of those pieces in turn. So my x plus 1s all cancel each other out. Leaving me with -1 over x minus 1 squared. Astute among you may have noticed that if I had gone back to this original expression, x plus 1 over x squared minus 1, that thing reduces. I could have reduced that fraction and called it 1 over x minus 1. If I had done that, the process of taking the derivative would have been a good bit simpler, but the result would have been exactly the same. Let's take a look at one more before I give you one to try on your own. Let's take a look here at the derivative of x squared plus 2x plus 3 over x minus 1. Right, this time, this fraction will not reduce. There's nothing we could do to save ourselves some effort. This is just going to be annoying. But we decide that f, our numerator, is x squared plus 2x plus 3. G, our denominator, is x minus 1. F prime will be 2x plus 2. G prime will be 1. And using the quotient rule, we're going to get f prime times g minus f times g prime all over g squared. And we'll substitute in what we have for all of those things. It's 2x plus 2 times x minus 1 minus x squared plus 2x plus 3 times 1 all over x minus 1 squared. Multiplying all of this out, 2x squared minus 2x plus 2x actually cancel each other out, minus 2, and then minus, well, I guess it's just minus x squared minus 2x minus 3. Combine some like terms. 2x squared minus x squared is x squared. We've got a minus 2x, and we've got a minus 5. X squared minus 2x minus 5 does not factor. So I can leave the result looking more or less like that. All right. With that in mind, here's one for you to take a look at. Using the quotient rule, evaluate the derivative of 2x squared minus 7x all over x plus 5. Take a few minutes, see where you can get to with that one, and I'll see you in the next video.